Besides single sideband AM modulation and DSB SC signals, double sideband suppressed carrier, we have quadrature amplitude modulation technique that so what happens in this quadrature amplitude modulation is that you can transmit two independent let's say double sideband suppressed carrier signals over the same channel, okay, provided that if you can multiplex, you can modulate the two signals with the same carrier frequency, but the carriers are having 90-degree phase shift. Okay, so for on the same channel you have two independent DSBSC signals which are modulated by the carrier of same frequency, call it omega c or whatever, but the phase difference is 90 degrees. Okay, so they are orthogonal. It's just like I and Q signals. So at the receiver, the phase of the beat frequency oscillator or local oscillator, select one or the other. So if you are going to transmit a carrier, a pilot carrier having low amplitude, low power requirement, to the receiver, if you're going to send this to the receiver is going to extract the phase information so that there is no phase error or the amplitude error that results due to the phase error and the beat frequency oscillation is mitigated. Okay, so this transmission of two signals with orthogonal carriers, multiplexing with orthogonal carriers, is known as quadrature amplitude modulation. So note that the carrier can be suppressed, but still retaining at least low power pilot carrier provides a phase reference for the receiver. Okay, so we need a phase reference for the correct phase and frequency carrier insertion into super heterodyne receiver, so that we don't have any error in the amplitude of the received signal. Okay, now let's have a look at this schematic. This is a QAM transmitter, and B we have a receiver. So let's say we have a audio signal. Let's call this X1T. Okay, and this is going to be modulated, or there is a, call it a product modulator whose output is a multiplication of the shifted carrier. So we have a 90-degree phase shift, okay, over here, so it's going to be multiplied by sine omega ct. So what we're going to have is x1 x1t multiplied by sine omega ct over here, right? So this is my first double sideband suppressed carrier signal. Why suppressed carrier? Because we're not transmitting any carrier with this. This is only the sidebands of the spectrum of x1t are shifted at plus minus omega c. Okay, so this is omega t. Okay, then the other signal is cosine omega ct. Okay, that multiplies, let's say, another audio signal x2t over here. So what we have here is at the output is the product of the audio signal x2 and cosine. So we have x2t, t, x2 of t. So x1 and x2 are different, multiplied by let's say cosine of omega ct. Okay, so that's what it is. So besides these two signals which are going to share the channel, so QAM signals carries two audio channels. We are also transmitting a pilot carrier. Okay, so this pilot carrier is being transmitted. So this is cosine omega ct over here, and this is going to be transmitted, added to the channel. So basically, what we have is this signal plus x2t cosine omega ct and plus cosine omega ct. Isn't that right? So this we are sending this pilot carrier for the phase reference. Okay, for the phase reference to the receiver, so that receiver has the correct phase and the correct frequency information. So these are three signals that are being transmitted. This is the pilot carrier. Okay, so basically we are transmitting two modulated signal. These are DSBSC signals. This is my first DSBSC signal. Then I have the second DSB signals. That is the output of the second product modulator or mixer at the bottom. So this is the second DSBSC. So this is my transmitter, okay, and that's how I'm producing a QAM, uh, quadrature amplitude modulated signal. Quadrature means that there is a phase shift of 90 degrees uh, that is modulating the first signal, audio signal. Okay, so now these three signals, they are transmitted on the channel. At the reception end, first of all, you look at the bandpass filter. It's a very narrow bandpass filter centered at omega c. So what it does, it reconstitutes the carrier of exact phase and frequency. So in practice, this carrier regeneration is almost always done with a phase lock loop. And just to avoid any phase errors in the reconstruction, you use a PLL. So that's a better alternate. So here you have a here again you reconstruct your actually cosine omega ct. That's your original carrier, okay, and then again at the receiver end you have this phase shift network which produces 90-degree orthogonal carrier frequency sine omega ct, and then you have the same signal cosine omega ct over here. Now, if you multiply this with the sine omega ct, you multiply sine omega ct with the QAM signal, which is otherwise x1. So if I can remove this t, I can just write let's write sine omega ct, sine omega ct, okay, plus I have cosine omega ct over here, sine omega ct. Cosine omega ct is reconstituted by the bandpass filter, okay. And then the second DSPSC signal was x2 cosine omega ct, okay, so orthogonal carrier. And if I'm going to multiply this with sine omega ct over here, well, my product yields x1 sine square of omega ct, sine square omega ct, right? And then I have another term plus cosine same omega ct argument multiplied by sine same argument omega ct, right? And then I have the third DSPSC signal, that is x2 sine and cosine, sine omega ct, cosine omega ct. So how do we extract the information that was originally transmitted, and how do we demodulate this? Well, you need a low pass filter over here, okay, to extract the channel 1 audio output you see over here. So basically, if you recall some trigonometric identities, well, this can be written as x1. If you recall, cosine 2 omega ct, cosine 2 theta is 1 minus 2 sine square theta. So this can be written as 1 minus, let's say, cosine of, I can write this as cosine 2 omega ct, right? And then the whole thing divided by 2. There is factor of 1 over 2 that comes over here, shows up over here. So we have a DC term and we have a high frequency term over here, okay? For this term, you recall that the same argument omega ct, actually this is omega ct, I just brief this as an argument by a dot. You must appreciate this is still omega ct, same argument. So you see sine 2 theta, if you recall, 2 theta is twice sine theta cosine theta, okay. And well, that's very easy to filter this out, because this is again going to produce a high frequency term which can be low pass filtered out, right? So you see over here, if you use this one and you can filter out this term, actually this term will be equal to half sine 2 omega ct, half sine 2 omega ct. I'll write this down over here. 2 omega c times t. Okay, a bit slow, but anyways, right. And what about this term? You see, this is again the same scenario over here. So again, we have this. So the high frequency term. So x2 by, so again 1 over 2 comes over here. Just like we can use this identity. Okay, we can bring 2 over here, and then you have sine of 2 omega ct, right? This is again a high frequency term. So what is missing in this depiction in this receiver is a low pass filter. So if I can append or add a low pass filter over here, my job is done. So let's use a low pass filter over here. It could be an RC low pass filter, an analog low pass filter. Okay, you might not need very high number of RC sections. Okay, it could be just a passive low pass filter without any op-amp gain. Anyways, so with a low pass filter, this term is going to go out. Okay, this term can be low pass filtered. This term can be low pass filtered. Okay, if you're going to even select the cutoff frequency of this low pass filter to be omega c. Okay, so cutoff frequency could be, or even you're going to, I mean, the cutoff should be the bandwidth should be at least equal to the bandwidth of x1t over here. Okay, so bandwidth of x1t. Whatever is the highest frequency that is contained in x1t, that will be the frequency. Okay, so the cutoff should be at least the highest frequency that is contained in x1. So as a result, my output for channel 1 is 1 by 2 x1t. Okay, that was transmitted as a DSPSC signal. The DSPSC signal, and that was my first DSPSC signal besides the second DSPSC signal. So actually over the same, or let's say, voice channel, we are sharing the channel for the two independent DSPSC signals, and for channel 2 output independently I am detecting 1 over 2 x2t. Basically you can do the same, you can use the same trigonometric relationships, and then you can multiply your QAM signal, which is this signal over here, the same signal multiplied by cosine omega ct. So at the output you're going to get x2t. All right. So that's how you get the two streams or two digital. It could be analog, it could be digital. This is analog QAM. So you share the bandwidth. Okay, you're sharing the the bandwidth requirement is low because you're sharing the same channel. Okay, to transmit x1 and x2. So basically, this figure is showing you this transmitter and the receiver, and how you can detect the first audio and the second audio signal for a QAM system. So here the receiver is using the narrowband filter. First of all, we have seen this narrowband bandpass filter to isolate the pilot carrier, and then amplifies it to obtain the reconstituted either beat frequency oscillator or local oscillator, depending on if you're using a super heterodyne receiver or a direct conversion receiver. Okay, so either you use super heterodyne or direct conversion receiver, and you're bringing back the spectrum to the baseband. Okay, so this bandpass filter actually reconstitutes the carrier with the correct phase and frequency information, and then you can extract your channel 1 and channel 2 by using maybe a low pass passive RC filter. So again, we will have a low pass filter, and this low pass filter will have its bandwidth or the cutoff frequency to be at least the highest frequency that is contained in x2. Okay, so the bandwidth of the second low pass filter will be the cutoff frequency is at least the bandwidth of x2t. Okay, note that x2t and x1t might have different bandwidths, right? So where do we use QAM? For example, the US NTSC and European Power Television standards for color television, they use QAM to transmit a pair of video color different signals. Okay, just like IQ transmission. So for example, in the NTSC system, These are so-called I and Q signals, in phase and quadratures, and they are multiplied by sine and cosine versions of 3.579 megahertz oscillator signals, and resulting DSP-SC signals are added to the normal video luminescence signal. Other uses of QAM include delivery of, let's say, digital television signals to set up converters in some cable television systems and data distributions in some LANs. So these are some of the applications of QAM. Again, the QAM system, they can be used for broadcast AM stereo with both left plus right and left minus right signals. So you have actually X1, for example, audio over here. You have X2 over here, and you can transmit them as two independent DSP-SC signals. For example, in a stereo they can be left and right audio signals. In televisions they can be different color signals. Okay, so depending on applications, you can preserve the bandwidth and you can send these two independent DSP-SC signals. So, for example, in AM stereo with both left plus right and left minus right signals fitting into the channel, they used traditionally for left plus right alone. Okay, so you can actually fit in the same channel left plus right and left minus right signals. However, the QAM stereo signals would not be compatible with the envelope detector as in standard AM receivers. Okay, so you might need a direct conversion, or you need, we are not using any envelope detector over here, right? So it's just like a direct conversion that you're multiplying this with cosine omega ct and you're bringing this x1 back to the baseband. Okay, so this is bringing back to the baseband, right? With using a BFO, that is the beat frequency oscillator or local oscillator, which has the correct frequency and phase information. You don't need envelope detection over here. It's just like a baseband detector, and the baseband can be low pass filtered out, as you can see in both channel output. Okay, so the QAM stereo signals, they are not compatible with the envelope detector as in the standard AM receivers. Okay, so these are just some few applications in television and in the radio broadcast standards used, standards that are still using the QAM to transmit the television signals or the radio signals. Okay.